Simply speaking, compressors can be seen as pumps for gases. However, with this broad application classification, one will need to include blowers and fans in this classification. Compressors are used to increase the pressure of gases, which we know are compressible fluids. There are a number of reasons why one would need to increase the pressure of a particular gas stream. The reasons would include transportation of gases, increasing partial pressure of gases to improve kinetics, solubility, etc. You can think of other uses that you have encountered in your particular work environment and other classes within the course of chemical engineering. There are two main types of compressors, which are the positive displacement compressor and the dynamic compressor. Positive displacement compressors can be further subdivided into two, namely the rotary and reciprocating compressor types. Within these categories, there are various examples and design configurations. For the dynamic compressor type, there are mainly only two design types based on the discharge flow direction of the fluid relative to the dynamic rotating part of the compressor. The third design type is just a combination of the two main designs, where instead of the flow of the gas going radial or axial, it's more of a mixed direction flow. This is just another picture from another source showing you types of compressors. A quick recap on these two types of compressors. The positive displacement compressors operate by trapping a specific volume of gas and forcing it into a smaller volume, by this compressing the gas, while the dynamic compressors operate by accelerating the gas and converting the kinetic energy into static pressure energy. Let us take a closer look at rotary compressors. These compressors get their name from rotating motion of the transfer element that is used to compress the fluid. The main designs of this class of compressors are the rotary screw compressor, sliding vane compressor, the lobe compressor, liquid ring compressor, peristaltic, scroll, and claw compressors. We will look at some of these designs in more detail in the next few slides. We will start with the rotary screw compressor. This is the most used compressor of this category in the industry. One common use is in the auto industry as a turbo machine in the turbocharged engines. It operates with two helical rotors that rotate towards each other, causing the teeth to mesh. As the left rotor turns clockwise, the right rotor turns counterclockwise. This forces the gases to become trapped in a central cavity. The two rotors are attached to the drive shaft, and the drive shaft provides energy to operate the compressor. Here is a short video animation from convergence training showing how the compressor works.
Rotary screw compressors are also positive displacement machines. These compressors employ two rotating, interleaved helical screws which capture air in a pocket between them. The space in which the air is trapped becomes smaller as it moves down the axis of the screw. The compressed air is discharged from the opposite end of the intake. Rotating screw compressors can be used in applications ranging from 3 horsepower to over 500 horsepower. They are commonly used by roadside repair crews to power air tools and are also used for automobile engine superchargers.
Next, in the design of rotary positive displacement compressors, we will look at the vane compressor. This design type uses a slightly off-centered rotor with sliding vanes to compress the gas as it moves within the chamber. Inlet gas flows into the vanes when they are fully extended and form the largest pockets. As the vanes tend towards the discharge port, the gas is compressed as the pocket becomes smaller. As the volume decreases, the pressure increases until maximum compression is achieved. Then the gas is discharged out of the compressor. The next design is the lobe compressor, which is characterized by two kidney bean-shaped impellers used to trap and transfer the gases. The two impellers move in opposite directions on parallel mounted shafts as the lobes sweep the gases across the suction port into the discharge line. The lobes do not touch each other. A very small clearance exists between the casing and the lobes. These compressors are designed to have constant volume, discharge pressure, and constant speed drives, and can be used as compressors or as vacuum pumps. Next in the design of rotary positive displacement compressor is the liquid ring compressor. This design has one moving transfer element and a casing that is filled with water or seal liquid. As the rotor turns, the fluid is centrifugally forced to the outer wall of the elliptical casing, and a gas pocket is formed in the center of the casing. As the liquid ring compressor rotates, a small percentage of the liquid escapes out of the discharge port. The makeup liquid seal is added to the compressor during compression. This liquid helps to cool the compressed gases. This compressor type is usually used where hazardous or toxic gases are handled. We will now move to the positive displacement reciprocating compressors. These are very common types of compressors, and they work by trapping and compressing specific volumes of gases between the piston and the cylinder wall. The back and forth motion incorporated by the reciprocating compressor pulls the gas into the suction or intake and discharges into the discharge vessel. Spring-loaded suction and discharge valves open and close automatically as the piston moves back and forth within the cylinder chamber. The assembly of a reciprocating compressor is shown here to indicate the building blocks. We have the piston, which moves back and forth to suck the gas into the compression chamber and compress the gas. The piston is connected to the driving crankshaft by the connecting rod. The crank is rotated by the motor drive. The piston rings seal to ensure that the lubricating oils do not leak into the compression chamber. The suction and discharge lines serve as inlet and outlet. Let's take the next few minutes to go through the workings of a reciprocating compressor in an animation video.
A reciprocating compressor compresses refrigerant vapor in a cylinder using a piston. In a way, reciprocating compressors are like automobile engines. The pistons are directly driven through a wrist pin and connecting rod from a crankshaft. Depending on their size, reciprocating compressors may have one or more cylinders. Multiple cylinders may be arranged in line, opposed, or in a V. In each cylinder, reciprocating compressors have both a suction valve and a discharge valve. These valves give the compressor its ability to pump refrigerant vapor against a pressure difference. They are usually located in the head of the cylinder, in passages connected to the high or low pressure side of the system. Let's follow the compression process in a single-cylinder reciprocating compressor during one complete revolution of the crankshaft. Starting with the piston at the top of its stroke, or at top dead center, the piston begins to move downward as the crankshaft rotates. Because both valves are closed, the downward moving piston reduces the pressure in the cylinder. As the pressure in the cylinder falls below the low side pressure in the suction line, the pressure difference opens the suction valve, letting refrigerant vapor flow into the cylinder. The piston continues down and pulls in more vapor until the cylinder is filled with low-pressure vapor at the bottom of its stroke. Once past bottom dead center, the piston begins its upward stroke. The suction valve closes. As the piston moves up, it reduces the volume of the space in the cylinder, increasing the pressure of the vapor. When the pressure in the cylinder exceeds the high side pressure in the discharge line, the pressure difference pushes the discharge valve open, letting the compressed vapor flow out of the cylinder. This continues until the piston reaches the top of its stroke and most of the compressed vapor has been expelled into the discharge line. When the piston begins its downward stroke, the discharge valve closes. The complete cycle then repeats during each revolution of the crankshaft. This is the mechanical positive displacement vapor compression cycle using a reciprocating compressor.
Okay, moving on. Now let us look at multi-stage compression using reciprocating compressor. If one compressor cannot achieve the required compression ratio due to some limitation, you can use a second compressor or even third and fourth to achieve the required compression. The progression used in multi-stage compression is that the compressed outlet gas from the preceding compressor feeds as an inlet to the next compressor. There may be need to cool the gas stream before it is fed to the next compression stage. Let us spend the next minute or two watching a video animation of a 4-stage reciprocating compressor.
Working of a V-type multi-stage reciprocating air compressor. A simplified model of a multi-stage V-type cylinder arrangement of a reciprocating compressor is depicted. There are 4 cylinders, namely the first, second, third, and fourth stage cylinders. A flexible coupling transmits drive to the compressor. The coupling is fixed on the crankshaft and also serves as a flywheel. A fan, driven by V-belt transmission, is mounted on the rear end of the crankshaft and provides external cooling to the cylinders and coolers. In this design, the first and second stage cylinders are of the trunk piston design, while the third and fourth stages are of the crosshead piston design. Compressor walk around showing the various components. The first and third stage cylinder cross sections are shown. Component nomenclature. First and third stage compressor working. Air from atmosphere is sucked into the first stage cylinder. Compressed air is discharged from the first stage cylinder and routed through an intercooler to the suction of the second stage cylinder. Compressed air discharged from second stage cylinder enters the third stage cylinder through an intercooler. Air is further compressed and discharged from the third stage cylinder and routed through an intercooler to the fourth stage cylinder. The final compression takes place in the fourth stage, from where discharged air is routed to an aftercooler. The description is a simplified extract from the air compressor tutorial developed by Yesyan Graphitek. The actual tutorial provides much more detailed explanations with a large amount of interactivity. The tutorial provides a detailed understanding on different dynamic and positive displacement compressors. Extensive graphics and animations, along with step-by-step meticulous explanations with interactivity, provides a very deep understanding and retention.
Okay, this concludes a detailed look at the positive displacement compressors. We will now take a look at dynamic compressors. As stated earlier, these compressors operate by accelerating the gas and converting the kinetic energy into static pressure. The two commonly used types are the axial and radial centrifugal compressors. Classification of dynamic compressors is based on flow direction of gas that is being compressed. That is, whether the flow is axial or radial centrifugal. For axial compressor, the gas leaves the rotor in an axial direction. For radial compressor, the gas leaves the centrifugal impeller in a radial direction. The fast-moving blades add kinetic energy to the gas. At the inlet, suction of the gas occurs due to the reduction in static pressure due to the acceleration of the gas by the fan blades. Here with some diagrammatic representation showing these two types of compressors. It is important to note the application regime for each of these compressors. For higher flow rates and lower pressure ratios, the axial compressor is preferred. For lower rates and higher compression ratios, the radial compressor makes a better choice. Let us now take a look at how the axial compressor works. This compressor comprises a rotor that has a row of fan-like blades. Rotating blades attached to a shaft pushes the gas over stationary blades called stators. These stator blades are attached to the casing. As the gas flow moves along the shaft in an axial direction, the gas velocity is increased by the rotating blades. The stator blades slow it down. As the gas slows down, kinetic energy is converted into pressure. In a multi-stage operation, gas velocity increases as it moves from stage to stage until it reaches the discharge. Multi-stage axial compressors can generate very high flow rates and very high discharge pressures. Axial compressors are usually limited to 16 stages due to temperature or material limitations. In the industry, axial compressors are used where high flows and moderate pressures are needed. Weight for weight, axial compressors are lighter and more efficient, also much smaller than their radial centrifugal counterparts. Let us now spend the next few minutes watching a 3D animation .
MAN Diesel & Turbo is the world's leading supplier of industrial axial flow compressors. Various types of axial flow compressors are available to meet the specific requirements of different industrial sectors. Depending on the frame size, a single axial flow compressor may have a suction capacity of up to 1.5 million cubic meters per hour and be able to compress this flow to a maximum pressure of 25 bar. For example, all the air inside the Cologne Cathedral, which at 516 feet is the third tallest church building in the world, could be exhausted in around 16 minutes. The basic design of an axial flow compressor is similar to that of a fan. Blades are mounted around a shaft. In order to increase the effect, several of these blade rows are arranged axially, one behind the other. This axial stage group is often combined in a machine with one or more downstream radial stages in order to further increase the discharge pressure. A compressor of this type, such as the AR Max 1 shown here, is known as an axial radial compressor. The axial and the radial part are mounted on a common shaft, and the gas, normally air, flows through them in turn. An intercooler can be installed in between, which increases the efficiency of the compression process. Let's now take a look at the axial stage group. As they rotate, the blades strike the gas, guiding it backwards and also compressing it. This process generates a flow along the axis. That's why the machine is called axial flow compressor. The outlet casing guides the compressed gas to the outlet nozzle. Compression raises the temperature of a gas, which in turn somewhat reduces the density and increases the volume. As the downstream compression process would require more energy, the intercooler reduces the temperature of the gas before it enters the radial part. Axial flow compressors are able to compress extremely high volume flows, but the maximum feasible pressure ratio is limited. On the contrary, centrifugal compressors can only process lower volumes, but deliver higher pressures. Since the gas in the AR Max 1 has already lost sufficient volume through compression in the axial part, the downstream radial part is perfectly suited for bringing the gas to a high discharge pressure. MAN Diesel & Turbo has been designing and manufacturing axial flow compressors since 1950. either in air separation, nitric acid production, as blast furnace blowers, or in refinery applications. These machines have been verified hundreds of times and proven over decades. Coal liquefaction is a future-oriented application that extracts synthetic fuels and other chemicals from coal. The process requires large amounts of oxygen. Large air separation units are therefore becoming increasingly important. To extend its leading position in this area, MAN has developed AirMax. This compressor train consists of an AR Max 1 axial flow compressor as a main air compressor, an integrally geared centrifugal compressor, and a driving steam turbine in the middle. In its blading, AR Max 1 combines for the first time the benefits of conventional industrial compressors with those of aero engine compressors. This makes it extremely robust, as well as uniquely compact and efficient.
The second type of dynamic compressor is the radial centrifugal compressor. In this compressor, the gas flow enters the impeller in an axial direction and exits in a radial direction. The gas fluid is forced through the impeller by rapidly rotating impeller blades. The kinetic energy from the rotating impeller is converted to pressure energy partially in the impeller and partially in the stationary diffusers. The diffuser consists of veinless space, a vein that is tangential to the impeller, or a combination of both. The vein passage diverges to convert the velocity head into pressure energy. Centrifugal compressors accelerate the velocity of gases, that is, increasing the kinetic energy, which is then converted into static pressure as the gas flow leaves the volute and enters the discharge pipe. Types of centrifugal compressors are the single-stage compressor, which compresses the gas once. This type of compressor is used for high gas flow rates and low discharge pressures. We also have multi-stage compressors, which takes the discharge of the preceding stage and pass it into the suction of the next stage. This arrangement of compressors is used for high gas flow rates and high discharge pressures. Let us spend a few minutes looking at the video animation of radial centrifugal compressors.
Let's examine the centrifugal compressor, which uses non-positive displacement vapor compression for compressing large amounts of refrigerant and are typically used in very large capacity cooling systems. A centrifugal compressor has three basic components: an impeller, a diffuser, and a volute casing. Large capacity centrifugal compressors may have two or more impellers or stages in the same casing. Centrifugal compressors are usually driven by hermetic electric motors. However, open-drive centrifugal compressors are also available for applications using steam turbine, gas turbine, or engine drives. The impeller is a rotating circular disc with curved blades that is driven at high speed by the electric motor. As the impeller rotates, it moves refrigerant vapor from the suction opening in its center to the outer edge using centrifugal force. The vapor enters the suction at a relatively low velocity and leaves the outer edge of the impeller at a high velocity. This means that the impeller transfers its rotational energy to the vapor, but high velocity does not relate to high static pressure. To achieve the desired pressure increase, or compression, the vapor must be slowed down, converting its velocity pressure to static pressure. That's where the diffuser comes in. As high velocity vapor moves radially outward through the diffuser, the flow area increases, slowing the vapor and increasing the static pressure. Some centrifugal models have diffusers with vanes or pipes which change flow direction and further slow the vapor. The volute-shaped casing collects the slow-moving, high-pressure vapor from around the diffuser and conveys it to the discharge connection of the compressor. Inlet guide vanes control a centrifugal compressor's capacity. These movable vanes are located in the suction opening. With vanes turned fully open, the compressor produces its full cooling capacity. As the vanes are closed, they reduce refrigerant flow through the compressor, reducing the capacity of the refrigeration cycle. In addition, capacity control in a centrifugal compressor can also be obtained by changing the rotating speed. This concludes our segment on the mechanical non-positive displacement vapor compression cycle